Hello, once again, my name is Brian Shoemaker. This is my CSCI 331 Project 4 video. This is a page replacement algorithm simulation. And without further ado, first I implemented a reference string generator, which you can see right here. That stimulates the realistic program behavior. The real program exhibits locality and they don't access memory randomly. My generator uses 5 parameters, and it's the virtual memory size, which is 1024 pages, locality size, active region of pages, the rate of motion, which is 200 references before shifting, the transition probability, and the starting position. The algorithm generates M references within a local region of size E, then either shifts gradually or transitions to a completely new location based on probability T. Going down to my algorithms here, I implemented all 4 required algorithms. First is my optimal, which looks ahead to see which page won't be needed longest. This is theoretical. It's impossible in real systems, but gives us a performance baseline. Coming down to FIFO, the FIFO maintains a queue and replaces the oldest page. It's simple but always efficient. Simple but not always efficient. I missed a word there. Going down to the LRU algorithm, as you can see, it maps the page to timestamps of last use. If memory is not full, just adds a page. If memory is full, replaces the least recently used page. And then down to second chance, we have enhances FIFO with reference bits and gives popular pages a second chance before replacement. Coming into my experiments in my build, I did run 3 different experiments. Experiment 1 is the varying locality size. And then I will upload my graphs also. As locally size increases from 10 to 400, we see more page faults because more unique pages need to fit in memory. And the optimal consistently outperforms others. A small 10 to 20. All algorithms perform similarly because the working set easily fits in our 64 frames. Coming down to experiment 2 here, varying transition probability T. The higher transition probability means less locality for the program, and it jumps around more. When T is very low, for example, 0.001, the programs stay local and all algorithms work well. As T increases, we see more page faults across the board. Experiment 3 is varying number of frames, shows the graph, which I will upload again. This is critical. More frames mean fewer page faults. With only 16 frames, even optimal has 3,600 plus faults. With 256 frames, we can see a dramatic improvement with just around 100 faults. The gap between optimal and others narrows as frames increase. In conclusion, my 5 key findings from my experiment. Optimal algorithms always produce the fewest page faults. The LRU typically performs close to optimal in practice. Second chance performs between FIFO and LRU. And the FIFO is simplest but often produces more page faults. Locality effects. Larger locality size for E generally increases page faults. Higher transition probability T increases page faults. And the more frames always reduce page faults. As you can see, it's been completed successfully. My files generated for plotting. Here are my experimental data, and I will upload all of that with the project as well. So if you have any questions, feel free to put them in the grade, and I will email you and answer them.